Hello everyone, welcome to this video. In the previous video, we started the analytic design of the motor, and in this video, we will be talking about the analytic calculations, and let's continue the analytic design. So the first direct dependent variable is the output torque. And the output torque is equal to the output power divided by the rated mechanical speed of the motor. The rated mechanical speed, angular speed, is equal to 2 times pi times RPS. RPS is revolutions per second, that is equal to revolutions per minute divided by 60. So I implemented this equation here. This is the RPS, RPM divided by 60. And this is the omega m, rated angular speed, mechanical speed, 156.6. And here you can see the value of the output torque, that is equal to 5.12. So our design should be able to deliver this torque, right? This is our goal. So let's check the value of torque for the Siemens motor and the WEG motor, our benchmark motors. You can see the value of rated torque here, 5.1 Newton meter, when the supply frequency is 50 Hertz. And also you can see the value of torque here in this table. Let me check. The value of rated torque is 0.509 kgfm, right? The unit is different from Newton meter, but we can check the value online. Let me check. Let's write here kgfm to Newton meter. And if I write here 0.509, right, kilogram force meter, you can see the corresponding value in Newton meter unit, that is 4.99, 5 Newton meter, right? So yes, the value of torque is 5 for the WEG motor, and for the Siemens motor is 5.1, the same number that we calculated here, the desired output torque. The next variable that we can calculate is the motor slip. As you know, in induction motor, the slip is defined as the difference between the synchronous speed and the rated mechanical speed divided by the synchronous speed, right? RPM S minus RPM divided by RPM S. The value of slip for our design is equal to 6.67%, right? I calculated the value of speed based on the synchronous speed and the rated mechanical speed that I have here. The synchronous speed is 120 times supply frequency divided by number of poles, as you know. So I calculated the synchronous speed and the synchronous RPS and the synchronous angular speed also here in this part of the Excel file. So here you can see the calculation of the slip. I think the value of slip is also reported should be reported in datasheet. You can see the value of sleep for the WEG motor, right? 4.33%, and also the value of sleep for the Siemens motor is higher because the rated speed of the Siemens motor is lower. If I set the value of rated speed equal to 1435 in our Excel file, as you can see here, the value of sleep is 4.33%, right? So our implemented equation in the Excel file is correct. So let's continue calculation of direct dependent variables. We have two parameters as we discussed in the course objective part. These parameters are here: desired efficiency and desired power factor. The value of desired efficiency is 72.1% and the desired power factor is 0.8. So when we set the value of desired efficiency and desired power factor, we can calculate the input power, right? Input real power, input volt-ampere, and input reactive power. As you know, the input power is equal the output power divided by desired efficiency. And the input volt-ampere is equal to the output power divided by desired efficiency times desired power factor. And the input reactive power is equal to input volt-ampere times SQRT of 1 minus the desired power factor square, right? So I implemented these equations here. You can see the input power, input kVA, and input reactive power. And also here you can see the units and values. So when we have the value of input power, we can calculate the line current, terminal current, right? The terminal current is equal to the input power divided by SQRT of 3 times terminal voltage times the power factor. So I implemented this equation here. The value of terminal current is equal to 1.88, right? I implemented this equation here. And also let's check the value of terminal current for the Siemens motor, that is equal to 1.88, right? When we have a star connection, the value of line current is equal to 1.88. Here we can select the connection, star or delta. So based on the connection, you can calculate the phase voltage, and also you can calculate the phase current, right? Based on the connection. You can set the winding connection here. So I set the winding connection to the star, and also as you can see, the value of phase current is the same as the line current, right? The value of phase current is equal to the line current when we have a star connection, and it's equal to the terminal current divided by SQRT of 3 when we have delta connection, right? I implemented this if condition here. This is the phase current, right? If B6 is a star, the phase current is the same as the line current, otherwise is equal to the line current divided by SQRT of 3. So let's check the value of line current for the WEG motor. Here you can see the rated current is equal to the 1.9 amps, right? When we supply the motor with 400 volts voltage in a star connection. So now let's calculate. So let's calculate other dependent variables. The next one is the phase voltage. The phase voltage is equal to the terminal voltage divided by sqrt of 3 for a star connection. And as you know, for the delta connection, the value of phase voltage is the same as the terminal voltage, right? I implemented this equation here because I selected the star connection. The value of phase voltage, the RMS value of phase voltage is equal to the terminal voltage divided by sqrt of 3. The phase voltage in my design, in my case, is 230, right? So we calculated the terminal current, phase voltage, and now we are going to calculate the coil current and coil voltage. As you know, sometimes we need to use number of parallel paths in the stator winding, right? To reduce the amount of current in each branch and also reduce the wire size, right? To make winding easier. So if we don't use parallel paths, the value of current in each strand, in each conductor will be high. So we have two options. We can increase number of strands, or we can increase number of parallel paths. So sometimes when the value of input voltage is low, the value of terminal current is high, and we should distribute this current into parallel branches to be able to reduce the wire size and use a logical wire size for the winding. Here you can see parameters related to the stator winding, like slot fill factor, number of parallel paths, and so on. Here, the number of parallel paths is equal to 1 because the value of terminal voltage is high and the value of terminal current is low, and we will not have a problem or an issue with the wire size. So I set this number equal to 1 here, and as you know, the RMS value of the coil current is equal to the RMS value of phase current divided by NP when we have a symmetric winding, right? In this figure, all coils are the same number of turns, and electrical parameters are the same, so we can write this equation. Sometimes you might see asymmetric windings for induction motors. So for those kind of motors, you should use more detailed equations to calculate the value of current in each coil. Here we have this equation for symmetric windings. I implemented this equation here for the value of coil current, and as you can see here, the coil current is the same as the phase current. The next variable is the coil voltage. Here you can see this equation. The phase voltage is equal to the coil voltage times number of coils per each phase divided by number of parallel paths. As you know, the number of coils for a single layer winding is equal number of stator slots divided by 2 times M. M is number of phases, right? The value of M is equal to 3, right? Because we are designing a 3-phase induction motor. For a double layer winding, number of coils is equal to NS, number of stator slots, divided by M. And for a single layer winding, we have the half of this value. You can see the winding of the Siemens motor. This is a concentrated single layer winding, right? This is a single layer winding, and number of stator slots is equal to 36. So 36 divided by 2 times 3 is equal to 6. So for this benchmark motor, you can see this calculation here, and number of coils per each phase, that is equal to 6 for our benchmark motor. Also, you can select the number of layers here, single layer or double layer, right? I selected single layer, actually the same as our benchmark motor. So the phase voltage is the voltage between this terminal and this terminal, right? Let me copy and paste it here. So the phase voltage is the voltage between these two terminals. And here we have coil voltage. So the number of coils in one parallel branch is equal to number of coils per each phase divided by NP, right? So the number of coils in one parallel branch is total number of coils per each phase divided by number of parallel paths. So finally, if I multiply this by coil voltage, this will be equal to the phase voltage, right? So we have this equation here. And in this equation, we know the value of phase voltage, we know the value of NP, we know the value of NCPPH, so we can calculate the coil voltage. You can see the value of coil voltage here, that is around 38 volts, right? So till now, we calculated a number of direct dependent variables, right? And from the next video, we will work on the motor output equation. We will derive the output equation, and we will start motor sizing, right? So let's continue in the next video. Thanks for watching.